Okay, in this video, we are going to graph rational functions, and this is challenging. There's a lot of pieces we need to be aware of to put together, so it is really important that we think about why we're doing what we're doing and why it makes sense mathematically and what that tells us, and that's going to make it much easier instead of just, memorizing procedures without understanding what's happening and then we forget them. We're going to really make sense of why we're doing what we're doing work. So be listening to those explanations because that is meant to help you on any problem you try to tackle with this concept. So the first thing you want to do is factor everything. So pause the video, factor the top and the bottom, and then press play when you're ready to move on. Okay, this one factored, we have g of x is equal to, in the numerator, we have the quantity x minus 4 times the quantity x plus 1 over the quantity x minus 1 squared, so x minus 1 times x minus 1. Now the reason we do this factor is because when we're finding some of this other stuff, that's going to make it easier. The first thing I'm going to find are the intercepts. So I'm going to find the y-intercept to start with. Now this is one of those things, if you think about what you're finding, it makes it a lot easier. So think about any graph, the y-intercept. You could have a line. You could have a parabola. That's a bad example because we can't see the y-intercept. Let's think about this parabola. Okay? When you are thinking about the y-intercept, and we're talking like x, y, we're finding the ordered pair. The y-intercept is always happening when x is equal to 0. It's going to be 0 comma something, okay, because it's on the y-axis. That's the whole point. So that means we're going to take 0 and plug it in for x, and then do the math, and we'll get our y-intercept. So again, for the y-intercept, we're going to plug in x is equal to 0. Now you can do it on the original or the factored one. I'm going to actually show you both. So I'm plugging it in for all of the x's. So on this factored one, I would have 0 minus 4. That is negative 4. I will have 0 plus 1. That's 1. Divided by 0 minus 1, negative 1. 0 minus 1, another negative 1. And then remember, this is factored form, so we're multiplying everything. So we multiply the top and get negative 4. Multiply the bottom, you get 1. And so the y-intercept is happening at negative 4. Or when x is 0, y is negative 4. Okay? Now I said we could plug it into either form. Like we could plug it into the original. And in fact, sometimes it's easier to plug it into the original for these intercepts. Plug it in here, 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 and here. 0 minus 3 times 0 is 0. Minus 4, negative 4. 0 minus 0 plus 1 is 1. So either one of those is going to work. Okay? Now same logic is going to hold true for the x-intercepts. Think about x-intercepts. So you can have a parabola. You could have a line. You could have a cubic function, whatever. Again, bad example because it's hard to tell where that goes through the x-axis. Let's do this line. Whenever you have an x-intercept and you're thinking about the ordered pair, the y is always going to be 0. You'll have some x comma 0, some x comma 0. That's what it means to have an x-intercept. So we need to plug in 0 for y. Okay, so we're going to have, in this case, y is equal to 0. Now y is the output. In this case, we're in function notation. So we're just going to plug in 0 for the entire output of the function. So then what we have is 0 equals, and then this is where the factored form is going to be more efficient. So use the factored form, divided by x minus 1 times x minus 1. So again, we're just plugging in 0 for that with the output or the y or whatever you want to, however you want to think about that. Now, when you're solving a rational equation, you need a fraction equals fraction, so I put 0 over 1. And then we can just do cross products. So 0 times the denominator is conveniently 0. 1 times the numerator is conveniently the numerator. So we have relatively easy things to work with. Now we got to think back to algebra. When you are solving a quadratic in factored form equal to 0, either this factor can be 0 or this factor can be 0. Because one of the factors has to be 0 to give a product of 0. So we have, what we actually have then, is we have x minus 4 is equal to 0. Well, add 4 to both sides, so x is equal to positive 4. Or we have x plus 1 is equal to 0. Subtract 1, so x is equal to negative 1. So the two x-intercepts are 4, 0. When you plug in 4, you get a 0. When you plug in negative 1, you get a 0. So those are our intercepts. At this point, I'm just going to go ahead and graph those intercepts. Now, whatever you get is going to determine what you're going to count by. Since my numbers are pretty small, I'm just going to count by ones. If I had gotten a y-intercept of 50, I wouldn't count by ones. I'd count by fives probably, maybe tens. So before I tick off my graph, make the tick marks or the scale, see what you get. So what we have is, we said we had an x-intercept of 4, positive 4, and negative 1. I believe that was correct. I want to go back. I already forgot. Positive 4 and negative 1, and then a y-intercept of negative 4. Okay? So there are my intercepts. Now comes the asymptotes. Now, when you're thinking about asymptotes, you want to be thinking, well, first of all, vertical asymptotes. It's values that x cannot be. Asymptotes are things that the function is going to approach but never touch. We know in math you cannot divide by 0. So we're going to take the denominator, I'm going to use the factored form, and set it equal to 0 to see what x cannot be. And that's always going to be your approach. Take the denominator and set it equal to 0. So we are finding the vertical asymptotes. So we take the denominator, which is x minus 1, times x minus 1, set that equal to 0. So if we have x minus 1 is equal to 0, then x is equal to positive 1. And then the same thing over here. So in this case, we only have one vertical asymptote at x is equal to 1. Sometimes you'll have more than one of those. So on my graph, what I'm going to do is sketch in this line at x is equal to 1, and that is a line that either the function is going to approach or part of the function is going to approach but never touch, would be that line x is equal to 1. Sometimes it's possible that part of the function will, cross maybe a horizontal asymptote, but, the function is going to approach this line but not touch it because the x values can never be that value. Okay, otherwise you'll divide by 0 and that's no good. Okay, so then for horizontal asymptotes, these are the ones that are, they're more abstract because the idea behind them is limits. So it has to do with what kind of numbers you're dividing in the function. Like, is this a big number and a small number, small and big, that kind of thing. So I'm going to refer to the notes that we took on this. So we're looking at horizontal asymptotes. And it has to do with the degree of the expression. So degree is the highest exponent. And that's going to tell us if we're dealing with big or small numbers, or maybe they're the same type of numbers. So think about, again, this is abstract, but I'm going to try to explain it the best that I can. So if you have a big degree over a small degree, so we're talking big number divided by a small number, nothing interesting happens. It doesn't approach a number. A big number divided by a small number, as x gets bigger and bigger, it's not going to approach anything. There's no horizontal asymptote, and that's what you would write down. If you have two numbers, top and bottom, that are the same degree, we call that same over same. And what essentially happens is the numbers cancel out, okay? And then what's left is the top, it approaches the leading coefficients, the top leading coefficient over the bottom leading coefficient. So in this example we looked at in class, essentially what happens is as x gets bigger and bigger and bigger, this and this will be about the same. So the difference between them is so small that they essentially cancel out. And then what's left are these leading coefficients. So in this case, 2 over 1, that's why we got a horizontal asymptote of 2. And then if you have a small number, a small degree divided by a bigger degree, so a small number divided by a big number, it gets really close to 0 as x gets bigger and bigger and bigger. And that's something that in class we looked at with Desmos. And if you want some additional clarification on that, we can definitely look at that. But these are the 3 situations you need to look at. So in our example, I am looking and we have a degree of 2 over a degree of 2. So again, essentially, this idea of limits is as x gets bigger and bigger, this is going to cancel out with this, and what's left are the coefficients out front. And in this case, it's just a 1 over a 1. Okay, remember in our in-class example, it was 2 over 1. So you look at those leading coefficients. And in this case, we said it's 1 over 1. So that means our horizontal asymptote is y is equal to 1. So I'm going to sketch in this asymptote at y is equal to 1. So either part or all of the function is going to approach that asymptote at some point. Okay, the vertical, they never touch because x cannot be that value, but sometimes with the horizontal asymptote, part of the function might cross that while another portion of the function might just approach it. So to know what's happening, we would have 2 options. One would be to plug in a bunch of numbers on our graph and see what happens, like plug them in to the original function, okay? But we have technology to see what's happening, so that's what we're going to do. So I have a couple of things I'm going to show you. The first one is on Desmos, just because it's easier to see. And here I graphed it, the original function, and we can see our x-intercepts at 4 and -1. That's what we found. Our y-intercept is at -4, okay? And then I actually graphed the asymptotes that we found. We found a vertical asymptote at 1, so we can see that this function in red approaches it, but never actually touches it. It just gets closer to it. And then I graphed our horizontal asymptote at y is equal to 1, and we can see that this portion on the right gets real close to it, but never touches it. And then actually the portion on the left does cross it. Rational functions have strange graphs. Weird things kind of happen. But once we graph it with technology, we can get an idea of what it looks like. Okay, now same thing, graphing calculator, just maybe a little bit less, a little bit harder kind of to see those values, but we get the same thing. One thing I would point out is you got to use parentheses, and I would type in the original function instead of the factored form so that you can group the numerator and group the denominator. And of course you have to use divide because fraction means divide. And then you can get an idea of what that function looks like. Some of your calculators actually graph the asymptotes. I don't know if that's helpful or not. Sometimes it just looks kind of messy. But whatever the case is, we can see from this technology kind of how to sketch in our graph. Okay, and this is just kind of, it's not going to look perfect, but it's a rough sketch. So we have this portion on the right that approaches this, and goes through this value and then approaches that y is equal to 1. Okay, I'm just going to double check that. Yep, that's what's happening. And then we have this portion on the left that also approaches the vertical asymptote, and then it, starts to cross that other one, that other asymptote. So, and it goes through our x-intercept. And this is going to be probably not the best because it also needs to go through y-intercept, and then it's going to go down. Again, rough sketch, but it gives us an idea of what that graph looks like. Okay, so to recap, because this is, there's a lot going on with this. Okay, so the idea is the x and the y intercepts. Think about what you're plugging in 0 for. Okay, and then you just do the math with either the original function or the factored function. For the x-intercept, it's going to be much easier to use the factored form. Graph those points. Vertical asymptotes. It's what the denominator can't be. Okay, the value for x that the denominator can't be because you cannot divide by 0. So you take the denominator equals 0 and solve. And then horizontal asymptotes are those idea of limits where you have those 3 possible situations. Okay? If you still have questions about, again, especially those horizontal asymptotes, be sure to see me. If you're having trouble getting your calculator to graph it, see me and we will get that figured out.